All right. I do want to talk about at least one of the problems on the exam. And that's the last one. So the last one gave you a bunch of random variables that were all normal 0, 9. And then it asked, well, first started with t was a constant multiple of the sum of the first 3 over, is that right? And then the square root of the squares of the next 5, is that right? I'm just trying to remember. Is that right? Or did I have x's and y's? I think that's right? Okay. All right. So the problem asks to figure out what the k needs to be in order to make this a t distribution. So again, remember, for t, what do we need? What does the numerator and what does the denominator need to be? Okay, it has to be a z over a square root of a chi squared over, it's degrees of freedom, right? Okay. So the first thing that we need to do is make a normal distribution on top and a chi squared distribution on bottom. And in particular, I need standard normal on top and chi squared on bottom, right? If I just look at the x1 plus the x2, yeah, sure. If I look at the x1 plus the x2 plus the x3, do I get a standard normal to start with? No. In fact, what is the mean's right? The mean of those is 0, but what's the variance?
I watch 900 movies.
It's good that they're watching soccer.
Chelsea sucks this year.
What is what's the variance on the top? What do you do with the variances when you add independent variables? I don't think we multiply.
Oh, wait, 1, 2, 3, 5 times 9.
I'm looking on top.
Oh, okay.
You got to add them, right? Yeah. So the variance on top is 27, right? I need to get that standardized. Remember, to standardize, we don't divide by the variance, we divide by the what? The standard deviation, right? So to get it to be a z on top, I've got to take that x1 plus x2 plus x3 and divide it by the square root of 27, right? That is normal on 0, 1. Okay? So that was the first thing, is I need to recognize what the variance is on top and then divide it out, or divide out the standard deviation to standardize it. All right, on bottom, same idea. You're going to think about the same idea, but remember, when we do chi squared, again, what distribution do you square to get a chi squared? A normal, but in particular, it has to be standard normal, right? So for each of these in here, for your x4, your x5, your x6, your x7, x8, I've got to standardize them first. They're not standardized, right? So what do I need to do to each of the x4, x5, and so on to standardize them? What do I need to divide by? If I'm going to standardize it, what do I have to divide each one by? Again, to standardize a normal, you have to subtract off its mean and divide by its standard deviation, right? So for each of those, I need to divide by 3 before I square, right? Right? So if I do x sub I over 3 squared. This is chi-squared of 1. Oh, hey, that's just ugly. Right? Again, the point for both of these is, remember, for your t distribution on top, you have to have a standard normal. That's why I divided by the square root of the variance here to make a standard normal, right? I don't have to worry about subtracting off the means because the means are 0. But I do need to worry about adjusting the variances, right, to standardize. So that's why we divided by the square root of 27 to standardize the top. I'm dividing each of the x sub i's by 3 to standardize each of the bottom ones, right? So when I do that here, we need, if I square each of the 3's, I get a 9. I can pull out a 9 all the way through, right? So far, we would have that the square root of 1/9 times the sum of the squares here. It's not square root, just the sum of the, I just want this part. The sum of the squares times a 9th is chi-squared of what? Well, each one is chi-squared of 1. So when we add them together, it's chi-square of 5, right? Because there's 5 of them. Right? So now to make this, the last piece to make this t is I need to divide my chi-square random variable by its degrees of freedom, right? So putting all this stuff together, my t has to be x1 plus x2 plus x3 over the square root of 27. That's to make it standard normal on top, right? Divided by square root of the 1/9 times the sum of the squares. And then divide it by its number of degrees of freedom. Now, if you simplify that, you will get square root of 5/3 times what the original t was at x1 plus x2 plus x3 over square root of the sum of the squares. So what does your k have to be then? In that original part, what did the k have to be? That piece right there, right? Right. But to get to that point, I really needed to see that you were standardizing the top and, well, standardizing the bottom too, making that chi-squared distribution. I saw a lot of the square root of 3's on the bottom. It was because people were putting square root of 3 on the, just in the denominator. That was not standardizing the numerator. Standardizing the numerator really is dividing by the square root of 27. All right. Second part. The reason why I'm going through all this is because we're going to obviously deal with these distributions more as we go along. So that's why I want to make sure we go through this and pay attention to what's happening. What was the second part? Making the other chi-squared doing, right? Because I had the y's as well. Is that right? It asks you to figure out an appropriate constant to make u, the y's, the u be the... Oh, yeah, the u be the chi-squared. Well, just doing the same stuff we just did in the first part, I need to standardize the x's first, right? Or, well, think about what would happen, what constant we need. So your u is, was it the sum of 8 of them? Is that right? Okay. All right. Well, again, I need to make those standard. Because when we square just a normal old distribution, a regular old normal distribution, I don't know it's chi-squared. It has to be standard normal when I square it, I get chi-squared, right? To make that square, a standard normal, I need a 3 in the denominator inside the square. Or I need a 9 in the denominator, right? So if I do 1/9 of u, I get that, don't I? And now I have standard normal squared, right? Standard normal squared. That gives me chi-square of 1 added together 8 times. So 1/9 u is chi-square of how many degrees of freedom? Is 8 because I'm adding 8 of them together, right? So then that goes to the next problem where it asks for the, what did I say, the 95th percentile of u. So if I want the 95th percentile, we need to look up first the chi-squared sub 0.05. That gives the 95th percentile of the regular old chi-squared distribution. I do not remember that number off the top of my head. I know, I'm slacking. I don't have the entire chi-squared table memorized. Because I'm going to waste time doing that. Chi-squared of 8 at 0.05 is 15.51. So that's your 95th percentile of a chi-square random variable with 8 degrees of freedom. Well, the chi-squared random variable that we have with 8 degrees of freedom is the 1/9 u. So to figure out the 95th percentile for u, what do I need to do? Yeah, just multiply by 9, exactly. So I just need to take, so the 95th percentile of u is 9 times the 15.51, whatever that number is. Does that make sense? We okay with that? I keep thinking you're drinking a bottle of milk. I see the white. I know. I see the white. I see the white thing around it. I keep thinking it's full of milk. You've taken several drinks, and every time I was like, "Oh, that's not milk." I don't know why. All right. Q is U over V. V looks a lot like U, except it's got 7 things squared instead of 8, right? All right, so since we're squaring a normal, as soon as you square a normal, you think chi-square, right? So I've got chi-squared divided by chi-squared. What kind of distribution is that, typically? It's an F, right? So I expect this to be an F, but I need the top and the bottom to be both chi-squares, right? And I also need to do what in the numerator and the denominator? Divide by the degrees of freedom, correct? All right? So I need to divide by the degrees of freedom in each of those. I also need to multiply each of them by an appropriate constant to make them chi-squared. But notice in this case, the constant on the top and the constant on the bottom, you would need to multiply by would be the 9th, like we did for the u to start with, right? To make u into a chi-square, we had to multiply by a 9th, right? I'd have to do the same thing for the v, so the 9ths would cancel. So I need to divide the top by 8, the bottom by 7, right? So we would have 7/8 q then is f of 8/7. That's owing to the fact that I have to put the 7 in the denominator of the denominator. Okay. So then for the 99th percentile of Q, I need to look up f of 8/7 in the table. 87 at 0.01 is 6.84. So we'll set that equal to our 7/8 Q and then do the same thing we did in the previous part. So that the 99th percentile of Q is 7/8 times 6.84. Mainly the point of the problem was making sure that A, you knew the definitions of your distributions, or what the forms had to be, and B, playing around with the constants. Or I was just being mean, one of the two. Right. Do you have other questions about test things before we talk about new things? I'm going to skip over sections 6, 7, and 6, 8 for the time being. We are going to come back to those later on. When I said skip over for the time being, you probably inferred that I meant that we would come back to them later. The reason for that is I want to get into some of this hypothesis testing stuff now. We're going to take smaller steps in the way we're approaching this. We're going to do some more of the conceptual stuff later on, making some of the theory work. But right now, we just want to kind of get the steps involved in what's going on with hypothesis testing, what the different definitions mean. Later on in the hypothesis testing stuff involves some of the stuff with the linear regression pieces, which is why I'm going to skip it for now and come back to it when we're actually going to talk about hypothesis testing for the different parts of linear regression. In particular, one of the things that we're going to be interested in, we've talked about least squares line last semester, where you figure out what the constant is, where you figure out what the slope is. One of the things that's important in least squares is to make sure that you've got a useful model. Part of that we talked about with the R squared value last semester. And we didn't talk a lot about it, and you've probably talked about it in other regression classes if you've had them. But the R squared is a measure of how good of a model you have. So one of the things that there's going to be a couple of different hypothesis testing we're going to be interested in later on this semester. One of them is your correlation actually something besides zero? There's going to be some correlation statistics stuff that our hypothesis testing will do. But also, is your slope actually non-zero? Or is your least squares line just best described by a horizontal line? You're going to do hypothesis testing on the slope. Okay, so those are a couple of things that we're going to talk about later on as we start introducing more theory into hypothesis testing, which is why I'm just going to put it on the back burner for now and come back to the regression stuff when we need it for hypothesis testing later. Okay, all right, so just to let you know why we were skipping ahead a couple of sections. So chapter 7 is about hypothesis tests. 7.1 talks about tests about proportions. So they give an example in the book of why you might be interested in doing such a thing. So as an example, they give a manufacturing process. And for argument's sake, let's just say that you're manufacturing light bulbs. Okay? And you know from past experience that for some reason you're a really bad manufacturer and 5% of your light bulbs are defective. Okay, so you want to get together with your engineering team, your manufacturing team, and develop a new process for constructing your light bulbs to try to cut down on those number of defectives. So you want to be able to tell whether or not this implementation was effective. Well, if you're going to implement a new process, you're probably not going to roll it out to the entire factory at once, because if it doesn't do any good, you've just done a heck of a lot of expense for zero reason, right? So when you do this, you're going to do it at a smaller scale. You're going to test it, and you're going to take samples and see what happens. Okay? So you're going to roll this out on a small scale, test your new whatever manufacturing process it is, pick out some light bulbs and see when they fail or if they're defective. And hopefully, instead of 5% of your light bulbs being defective, maybe 2% of your light bulbs are effective. Or defective, not effective. You want more than 2% of your light bulbs to be effective. Okay? But from that perspective, did you test enough light bulbs? Is it possible that your random sample of only two were defective out of 100, say? Is that a big enough sample? Or do you need a bigger sample to say, no, my change really was effective. I don't have as many defective light bulbs anymore. I've got a lower percentage. Okay? So this is why you want to know hypothesis testing. Is the sample that I chose enough evidence to say that change was effective, or enough evidence to say the means of two populations are different? Or is there enough evidence, not enough evidence to say that your variances are not equal? Remember, one of the assumptions we made for one of our hypothesis testing was the variances needed to be equal in order to use this t-distribution, right? So you might be testing whether or not variances are unequal. I just alluded to, if you have a linear regression model, you might want to know that your slope is not 0. Because if your slope's 0, then why wouldn't you just use this point estimate and call it good, right? If your slope is 0, saying, I've got this model and it's the same value for anything I plug in, is a crappy model, right? So there's lots and lots of these different scenarios that you're going to want to test one statement versus another. All right? So this is where this stuff is coming from. So, all right. So we want to talk about doing hypothesis testing. So in your hypothesis test, there's two statements. You've got an H naught and an H sub A. The H naught is what's referred to as your null hypothesis. Your null hypothesis, your book refers to it as kind of your no change hypothesis. This is what I like to refer to as the status quo. This is what we think is going on now, or someone thinks is going on now. One of the things that I gave you on the test, when you found that proportion confidence interval for percentage of people who pass exam P on the first try, your status quo in that case in the part B would have been that they claim that 40% of the people pass exam P on the first try. Right? That's the status quo idea. The confidence interval is a way to kind of test that status quo. You were asked on the exam, does that seem like a valid statement for the Society of Actuaries to make? Well, you're checking to see whether or not the 0.4 was in that interval. Okay? This is going to be another way to kind of check the same idea, just not doing confidence intervals perspective. Okay? All right, so that's kind of the status quo, or what's being purported to be true. Your H sub A is what's referred to as the alternative hypothesis. This is the it's an alternative. It's the, I'll call it the change hypothesis. I don't know, for lack of a better word. It's the non-status quo hypothesis. Was there a change from the status quo? Status quo is what's going on now, or what's assumed to be going on now, or what we've done from our manufacturing in the past. The alternative hypothesis is the status quo true? Or has the status quo changed? Is it different than what it was before? Okay? Now, in the proportions scenario, we really are thinking about this as, I think the proportion is this. Do I want to see if it's changed off of that? Okay? So in typical statements, your null hypothesis is that your population proportion is actually, in fact, equal to a certain percentage. That's what's typically referred to as a simple hypothesis. When the population parameter is said to be equal to a specific value, that's a simple hypothesis, whether it's the null or the alternative. Okay? So a simple hypothesis is that the population parameter is equal to a specific value.
We could use any parameter.
Yeah, any parameter. It doesn't matter what the parameter is. Now, for our purposes in this section, it's going to be proportions. In the next section, I might start the next section today, but the actual concept I want to talk about, I won't get to it until Wednesday. It could be the mean is equal to a specific value. It could be the difference of the means is equal to a specific value, typically 0, because you think about the means being the same. Okay. Variance could be equal to a specific value. Variance could be equal to each other, those kinds of things. But the simple hypothesis part is the fact that it's actually identically equal to something, okay? Not in a range of things. That's what we mean by a simple hypothesis. Okay? Ordinarily, your null hypothesis is stated as a simple hypothesis. 40% of people pass exam P on the first try. 35% of people approve of the job the president's doing. Those kind of things are simple statements. Is this, right? Is equal. Okay. When you're thinking about making a change, like the manufacturing example, 5% of the light bulbs that we produce are defective. That's inequality. That's a simple hypothesis. If you're going to make a change, you're trying to move off of that hypothesis, not making a statement of this specific proportion now is the new status quo, but just that you've hopefully reduced the number of defective light bulbs. Okay? That's a compound hypothesis, not simple. If I'm going to move off of the value equal and move into a range, that's a compound hypothesis. Your alternative hypotheses are typically compound hypotheses. Compound in the fact that I just want to know that the status quo has changed. Not to what it changed to, not a specific value that it changed to, but that it moved. Okay? So either it's less than what it was before, greater than what it was before, or not equal to. There's 3 possibilities in that, right? Okay.
So we make these hypotheses on 2 different samples.
We make these hypotheses. You make your null hypothesis is what you already assume to be true. So that's not based off of a sample. That's based on either years and years and years of prior knowledge or a guess. And you're just trying to see if that guess is right or wrong with the sample, right?
Oh, okay.
Yeah. Yeah. So, for example, maybe you are developing a new weight loss program.
Okay.
So you already know the weights of the individuals coming in.
Okay.
And then they go through the weight loss program and you take a sample of them and see what their weights are afterwards. So you only do so your status quo was what their weights were to begin with.
Yeah.
Okay. Or another idea of someone thinks that 70% of the people in the country approve of the job Congress is doing. And you want to refute that statement.
So then I take a new sample.
Yeah, you take a new sample and refute that statement. Yeah, that's the idea. Yeah. All right. So just to write this down again, then your simple hypothesis is equal to a specific value. Null hypotheses are usually stated this way. Okay. The null hypothesis is usually a simple one. So a compound hypothesis is just one that gives you a range of possible parameter values. And this is usually what your alternative hypothesis is stated as. Now again, there's a specific concept that we're going to talk about on Wednesday where we're going to actually have only two alternatives. Either it's the null hypothesis that's equal to a value, or the alternative hypothesis is equal to a different value. One of the reasons why we're going to do this in a very specific case is because there's a couple of concepts that come up in hypothesis testing. In particular, when do you screw up? When do you make an error? That are nice illustrative examples when you've got simple hypotheses for both. So, all right. So, in our manufacturing process example, the idea is that we wanted the manufacturing process to make a change, right? So we want to say, I know that I know, quote unquote, know, the null hypothesis is false and the alternative hypothesis is true, so that I can say that my manufacturing process made the appropriate change. Now, why did I say quote unquote no? Well, anytime you're doing anything from sampling, you don't know for a fact, right? You know up to a reasonable certainty. Okay? There's where the confidence levels come up again, like we did with confidence intervals, right? We know for reasonable certainty that the mean must be between these two values because we randomly picked a sample that generated this interval, and that interval that we generate from a random sample should contain the true mean or whatever parameter we're looking for a certain percent of the time. Right? So those confidence levels allow us to say, okay, the null hypothesis must have been false, therefore the alternative hypothesis must be what we want. Right? That's the idea. So, but there's still errors that might happen. We might have just gotten unlucky and picked a sample that said, hey, yeah, right, the null hypothesis, that's totally wrong. But it really isn't. Okay? That's what we refer to as a type 1 error. When you reject the null hypothesis, we call it rejecting when you just say it's not true. When you reject the null hypothesis and it's actually true. So we'll just write this down. The type 1 error is that we reject the null hypothesis when it's in fact true. Again, that's kind of the unlucky thing. Usually when you're setting up these, well, as researchers, you shouldn't have opinions, I suppose, one way or another. But if you think about it from a manufacturing change standpoint, if you made the manufacturing change, you're making it for a reason. You want to reject the null hypothesis in that case, right? Now, again, the statistician shouldn't have anything invested in whether or not it's true or false. It's just testing on whether or not you can reject it. Okay? But again, from a company standpoint, you want to be able to reject that null hypothesis if you made the change. You're making it for a reason, right? So that type 1 error is the probability that you made the change and shouldn't have, or made the change for no reason. Okay? Okay? So again, the idea here is that you want to try to minimize that, well, both types of errors you want to try to minimize. But at least from the type 1 error perspective, you want to try to minimize that thing by making your confidence level high, making that probability of that actually happening small, right? So thinking about it from a picture standpoint, let's say we have a normal distribution in here. Say, I'm going to do it in terms of means, even though we're talking about proportions right now. But this would be your mean, right? And you come along and find an X bar that's up here, up in the tail, right? Well, you want to pick a level, wherever that level is, so that this area is unlikely, right? You agree with that? So this is your confidence level. We typically refer to it as your alpha, like we did with the confidence intervals. Right now I've got this written on the high tail. Okay. So this alpha is equal to the probability that your sample mean is actually greater than whatever this value is. Let me call it, I'm going to call it Z at this point.
Should they have alphabet too?
It depends on what kind of test we're doing. You're right. Yeah. Yep. In the confidence interval stuff, when we did two-sided, it was alpha over 2.
So what are we trying to do here?
I'm trying to make this probability small. I want to come up with a region so that the probability that my sample mean landed in that region. So actually, the way I wrote this, I should write it as standard. I'll write it better later. I'm not going to worry about it right now. The probability that my sample mean landed above this value is actually equal to alpha. So I'm picking a range in my intervals. And so I'm going to write down what the hypothesis test would look like in this case here in a second. But I'm picking a range of values where the probability that I actually land in that range of values by random chance is small. That's what the alpha is. Okay? So in this case, the way we'll be writing this hypothesis test is that, let me actually make this a mu naught. The hypothesis test would say that the mean of the population really is that mu naught. So that your alternative hypothesis is that the mean is actually bigger than that. There's nothing there. I lost my pointer. Okay. Probably the same place where my mind is. Anyway. All right. So null hypothesis, alternative hypothesis. This alpha is describing a region in which I'm saying if I got this sample mean, now we're doing this with proportions. I know we started with those proportions, but the words are all the same no matter where we are. I'm picking this region so that the probability of landing in here is small if my mean really is mu naught. Okay? That it's a lot more likely that this sample came out of a higher mean than mu naught. Okay? That's what the alpha is describing. Okay? I'm defining a region ahead of time. Okay? Defining a region ahead of time that says, if I take my sample mean or my sample proportion or what have you, okay, whatever that is, the likelihood that it landed in that, given the fact that I had this other value already prescribed, is very, very small. So that must not be true. It must have been some other value, in this case, which is bigger. Okay? That's the idea behind this. Okay? So, again, that's why we call it this is an error. If I actually do find that sample mean up in that region that really did come from a distribution with a mean of mu naught, that's an error, right? I will have rejected it for no reason. Okay?
What would be the error?
Well, the error would be if I said this is not true, but it really was. If I really did find a random sample where my mean landed up here,
yeah,
but it really was true. But I'm saying that it's probably not true because it's very, very unlikely to have happened.
Oh.
That's where the error comes from. So say, for example, you had a mean, you thought the mean was 175. You came up with a sample and the mean was 250.
Yeah.
And the probability of that happening was like 0.003, say. You'd say, oh, then the mean's probably not 175. It's probably something that's bigger than 175.
Yeah.
But it really turns out that it was 175. So you made an error in rejecting it.
So what happens in the cases where if I take a sample and the mean of the sample is a bit smaller than mu naught?
Oh, in this particular case,
Yeah.
you wouldn't reject it then, because of the way you've got because in this hypothesis test we have it set up to where we're saying it was either mu naught or it was greater than mu naught. Yeah. There are some books that make the distinction of that they would add a null hypothesis is that you're actually less than or equal to here. But they would still call that a simple hypothesis, even though it looks compound. It's the one that actually contains the mu naught. The mu naught is what we're really trying to get rid of. And we're interested, did we go bigger? Well, if you found a random sample that was smaller, then it didn't go bigger. So you still just say you just do not reject the null hypothesis. Okay. All right. This region up here that we're interested in. Hello? Interesting. Oh, it's because that popped out. Oh, there we go. This region up here where we're trying to reject the H naught. So if we land up in this region, we refer to this region here as the critical region. Now, it's possible that we'll have critical regions on both sides, because if you're just interested in there was a change, you didn't care if it was positive or negative, it's possible you'll have regions on both sides. The way I've described this in this case, where I just had a region on one side, this is what's referred to as a one-tailed test. Okay?
But the critical region will depend on how small the probability is.
Correct, yeah. The critical region is dependent on the alpha you choose. Yeah. Okay. So a one-tailed test is the critical region is on one side of the mean. One side of the population parameter. It doesn't have to be a mean. Two-tailed is on both sides. Ooh, hey, that went crazy. In the two-tailed test, if you're using your alpha as your level of rejection, your rejection level, then you would split the alpha into two, and you would have alpha over 2 in each piece. So if you've got a two-tailed test, and your critical region is on both sides, then you would put alpha over 2 on one side and alpha over 2 on the other. Because again, you want the total probability that you reject H naught when you shouldn't to be alpha. Okay? Does that make sense? Okay. All right. So alpha is tied to the chances that you make a type 1 error. Okay. There's another type of error that you could make. That's referred to as a type 2 error. This is not rejecting H naught when you should. This is the alternative hypothesis is true, but you didn't get that from your sample. Okay, so your sample didn't lie, the sample that you got didn't lie in your critical region, so you couldn't reject the null hypothesis. To tie that back to a test question with the Society of Actuaries one again, if you came up with your confidence interval for the proportion, I believe your high side was 0.406, somewhere around there. So you couldn't say that 0.4 was not possible, or at least unlikely, because 0.4 was in the interval, but it was darn close, right? Okay. But what happens if it really was 0.4 was wrong? Well, then you accepted your null hypothesis, if you will. You didn't reject it, because your null hypothesis was the proportion is actually lower than that, but you didn't get a sample that was low enough, right? Your sample was 0.334 or something like that. I can't remember the exact decimal. Doesn't matter what it was. The sample that you had was a sample where the proportion was less than 40%, right? But you didn't have enough evidence in that case to say, oh, I can go ahead and say it's not really 40%. So in that case, you didn't reject the null hypothesis when in fact it might have been false. And you wanted to reject it. Okay, so that's a type 2 error in that case. We have a name for the probability. So the probability of making a type 2 error is referred to as beta, is called beta. It's the letter we give to it. What's tied to beta is what's referred to as the power of a hypothesis test. It's 1 minus the probability that you make a type 2 error. Power means that you reject the null hypothesis when you should, right? So the probability that you didn't reject it when you should, that has something to do with the power. So you want the probability of making a type 2 error small so that your power is high. Okay? This is something we're going to talk about later a lot more. We're going to talk a little bit more about this on Wednesday. But this is something we're going to talk about a lot more later because actually figuring out the power of a test is a hard problem. Okay? So what we have to try to do later on is form the most powerful critical regions that we can. Okay? That's a hard problem to answer. Okay? We're going to see why it's a hard problem to answer on Wednesday. But we'll talk a little bit more about trying to answer that problem later this semester. But know that you get to define the alpha. All right? So that part's easy. Figuring out the power is hard.
It's in the exam problem we had. Since we created the interval at 95% common interval, what is the power of making the type 2 error 0.05? Or isn't that?
No, that's not that simple.
Because it could be the case that
that's the 0.05 is the probability of making a type 1 error.
All right.
Right. Yeah, it's the type 1 error. It's not the type 2. The power is harder. Significant.